Okay, this is the fourth video for section 10.2. Um, I just want to introduce some specific types of simple graphs. Remember that simple graphs are no loops, no multi-edges. So some types. First of all, cycles. A cycle is just some number of vertices, and they are all connected in like a big loop. So going around from one to the other. It's like you took a string of vertices connected and then just tied them together. So the way we denote the cycles is like with C subscript and then the number of vertices. So C3, C4, and C5, C6, C7. Those are cycles. Wheels are basically cycles with a single additional vertex in the middle and then spokes going out. So there'll be edges connecting that central vertex to every vertex in the cycle. So ironically, or sort of strangely, I guess, the wheel W3 actually has 4 vertices. That number does not correspond to the number of vertices. So there's W3, W4. There's the 4 cycle with a 5th vertex in the middle, and edges connected out. So those are wheels. And then complete graphs. Complete graphs are graphs on the so it's a graph that has the maximum number of maximum number of edges while still being a simple graph. So basically every vertex is adjacent by an edge to every other vertex. So just kind of coincidentally, K3, K for complete as opposed to C for cycle, but K3 is exactly the same as C3 because that is already the maximum number of edges you can have. K4 looks a little bit like W4, except I want to make an important distinction between these two. In W4, there is a vertex in the center here, an actual 5th vertex where the sort of lines appear to cross each other. But in K4, even though I've drawn this graph such that those edges cross each other, there's no vertex at that crossing. Okay, they're just drawn so that the edges cross over. Now that I could have drawn it differently so that the edges don't cross over, just to kind of make this point a little clearer. Let's redraw this so that one of these edges goes through the middle, but the other one can wrap around the outside. And so this idea of like edges crossing each other doesn't mean that there's a vertex there. Okay, so just be very, very careful of that. If you are in the team that is working on graph coloring and planar graphs, then the idea of edges crossing each other is very important. There's this notion of a planar graph, which means that it's possible to draw the graph with no edges crossing each other. So K4 is an example of a planar graph because I redrew it like that. K5 over here, this is a complete graph on 5 vertices. I like to think it looks like you're summoning a demon or something. This, by the way, is an example of a graph that is not planar. So it's actually impossible to draw this graph without having edges crossing each other. Try it if you'd like. You can try to pull some of these edges out of the center, like pull them out here so that they do that instead. And it's impossible to do that without eventually having edges cross each other. All right, so those are just a few types of graphs that we'll mention later. And if you see this notation come up, then you know what it means. By the way, real quick question. How many edges are in Kn? How many edges do you think are in Kn? That would be the complete graph on n vertices. There's a quick and easy formula for that, but I want you to pause the video and take a minute to think about it. See if you can figure that out on your own. It uses a formula that we learned back in chapter 6. All right, so the answer here is that it is n choose 2. Take the n vertices and look at all of the different ways that you can select 2 of them and count those. That's n choose 2. But that is also all the different edges that you would have in the complete graph, because every edge is just two vertices connected. So there you go. It's kind of a neat little fact.